So we'll carry on from where we finished yesterday. So we were going through talking about matching and saying how this is quite a powerful aspect of the Rust language. Uh, and we had the example here where we're matching an option against the possibilities that an option enum can take, but also the fact that we can introduce variables within the pattern and then refer to those later when we do the expression on the right-hand side of the pattern. I've got another example here as well, really doing the same thing where we are matching, and this is matching and doing a division as well, and then it prints out different results depending on whether it was trying to divide by 0 or not. So it sort of takes care of that potential problem. Okay, so we'll finish off this part of the lesson just talking about how to install Rust if you don't already have it. Then the easiest way is via the tool called RustUp. There's the command you can run on Mac or Linux to do that, or if you're on Windows, then there's links there to do that also. It should be straightforward. I don't really ever have any problems with installing that. Now, when you install that, what it installs is a tool chain. So as well as the libraries themselves and the language, you get some tools. The most important of which is called Cargo, and this does a number of things. It acts as a package manager, so it allows you to specify and manage dependencies within a project. You also use it to build your code and also to make packages if you're going to distribute those. I've listed out here some of the common cargo commands so you can see those. So we can use it to build projects. We can use it to create a project. So this will set up a simple project with some boilerplate code for you so you can see how the project is laid out. You can use it to test your code as well. Let me move on to lesson 3. And to start with, I want to introduce you to the command line tools that are available on Solana. Now, one thing we're going to say a few times about how you install tools that we're going through is that you can install them locally, and that might be fine, but not everybody wants to do that, and there may be restrictions on your laptop if it's a work laptop, etc. There may be restrictions on what you can install. So if you can't do that, or if there are problems with the installing the tools, what I suggest is you use a Gitpod environment, and you can use this. This gives you a little Linux environment, and it gives you VS Code, and it's all in the browser. So you can use that and install everything on there. And you can do that from a repo. So it means you can save your code as well. So that's a useful alternative. And we know we have tested out everything that we're demonstrating within that environment so that we know that it should work okay. All right. Now, yeah, this is details here of how to install the command line tools. We when we put out these commands, we try to make sure that the versions are okay. Sometimes it turns out that there's a problem with maybe the latest version, or there's a clash between versions. So if you do have a problem installing any of the tools, let us know, and we'll try to work out how to a version that will work generally. But there's different instructions here depending on the environment you're in, so the operating system you're using, so Linux or Windows or Mac. But once you've got the command line installed, then you should be able to type Solana -- version, and then that will show that it's been installed correctly. It'll give you a version number, and you can also get help there. We need to set up some little pieces first of all to be able to use the command line to be able to do useful things. The first one is to set up a key pair, and so there are different ways that you can set up a wallet in Solana. Obviously, you can have a browser wallet. You can get a extensions to have a browser wallet, but you can also set up a file system wallet. So that is what this is doing here. So this is setting up a wallet within your file system, setting it up locally. So then you can use that with the command line. And so I've just got the commands here of how to do that. So you need to make a directory to uh, for the files that it's going to create. Then you run Solana keygen new, and then you specify a name of the JSON file that's going to hold details of your key pair. That will create you the key pair. You can check the results of that. You can display that and verify that. And this will give you an address, so you can verify that address against the file that you've got there. Once you've got that, then you can start to connect to network. So here's an example of how to connect to the dev network. So with Solana config, this allows you to configure your local environment. So what this command here is doing is setting up the environment so it's going to connect to the dev network. Obviously, there are different options, different networks you can connect to, but this is a useful one to connect to initially. If you want to check which network you are connected to, you can do Solana config get, and that will tell you. And once you are connected to a dev or test network, then you can get an airdrop. You can get some tokens. So if you do Solana airdrop 1, tell it the address of your wallet, where you want to receive those tokens. And either if you're already connected to the correct network, that should work, or if you need to specify the network to connect to, you can also specify the URL there, and that should give you an airdrop. Sometimes that doesn't work perfectly. You have to be patient sometimes, but that should airdrop some tokens to you, and then you can use those when you're developing. The airdrop itself will obviously create a transaction to move those tokens. So you can then look for that transaction on the block explorer, see what it is doing. That's a useful thing to do. And also, if you want to check the balance of your wallet, you can also do that with Solana balance and then your account address. And if you need to specify a different network, you can also do that. Okay. Once you've got that set up and you've got some Sol in your wallet, then you can try transferring that to other accounts. So try transferring some to your teammates. So there's the command to do that shown there. Where I've put key pair here, this is the path to the file system wallet that you're using. So that should work. And then if you want to check your balance, you've already seen that. You can do that as well. So do try that out. Try sending some Sol to your teammates. Okay. So let's go for the last half hour. We'll continue on talking about Rust and this phrase idiomatic Rust. This is all about the fact that the way that you write your code when you're writing Rust may differ a little bit to some of the patterns or the way that you've written code in other languages. So all languages will have a idiomatic way of a set of good patterns really for writing code in that language, and Rust is no different. And so we're going to try to show you some of those, but as you get more experienced, obviously you'll get to learn those as well. So you'll probably find that the way that you write the code, the patterns that you use will change over time, and you'll find more efficient ways of doing things in Rust. Now, I did say that one of the features of Rust is the fact that it manages memory without a garbage collector. And I just want to mention that again, this notion that we have the heap that is where we store large items in memory. And we have to make sure that that is kept, is freed up so that we want to make sure that it is updated and that items do not exist in, are not kept on the heap longer than they need to be. The other place that things can exist is the stack, but that's only for very small or simple items, and then that's managed automatically. Um, so we need this way of making sure that items that are in on the heap are still valid, and that we need to understand the lifetime of the objects that we're creating, the variables that we're creating. And the way that Rust does this is to impose a set of rules upon you so that the compiler can then use that to work out the lifetime of the objects that are going to be on the heap. So this is really, I think, one of the larger parts of the learning process when you're learning Rust is getting to understand these rules and to understand how to write your code so that the compiler will understand the objects that you are creating and the variables you are creating. And so what we'll see as we're going through the language and writing programs, you'll see that there are restrictions on what you can do. And when you're trying out code and writing code, you'll find that the compiler will come up with errors saying that you can't do things in a certain way. And hopefully it will try and direct you to a correct way of writing the code. But I hope, I'm sure you'll quite quickly get used to the way that you can write code correctly, and you'll get the hang of it, and it will make a lot of sense for you. But Rust is a little bit different in that it does impose these rules at compile time. So there is perhaps more that you need to know at that point. Whereas with other languages, maybe your code would compile okay, but then you would find that when it's running, it would throw errors. Whereas with Rust, you tend to get shown the errors straight away by the compiler, and then you have fewer errors once your code is compiled correctly. Okay. So to continue that theme, we need to talk about the concept of ownership. And this is all about understanding and controlling the lifetime of objects efficiently. And we don't want to get into some problematic areas. One of these areas is a thing called dangling pointers. What that means is that we have some kind of pointer to something in memory, but that thing in memory has maybe been removed, or maybe it has been overwritten by something else. And so we may be trying to refer to something in memory, and we think that we're referring to one thing, but actually the thing in memory is something different because of the way that memory is being managed. So we want to make sure that we don't get into that situation, because obviously that would introduce bugs into our program. Um, we also want to ensure that we don't run out of memory, that things are being overwritten or removed from memory when they are no longer needed. And so to enforce that, to make sure that that works correctly, one of the concepts we need to get used to is this concept of ownership. And in Rust, when we speak of ownership, we mean that a variable owns a value. So if we look at this line of code here, on the left-hand side, we've got a variable called myvec that we are declaring. We've declared it as mutable, but that's not relevant in this case. It's the ownership works the same anyway. And then on the right-hand side, we've got the value that's going to be uh, associated with that variable. So on the right-hand side of the equals here, we've got a vector being created, and we've put three values into it. Now, in other languages, you probably tend not to think of these things as being different in any way. We just need to think of it as a whole, perhaps. But in Rust, it's important that we realize that we've got sort of two things here. So we've got the variable itself, which is myvec, and then we've got the value that is uh, referring to, or that belongs to that variable. And we say that this variable then owns this value. So my vec is the owner of the vector that we've created on the right-hand side. And when that vector gets created, because it's a large complex object, that will be created on the heap. And so that is, we need to understand and be able to manage the lifetime of that vector. And that ties in with the lifetime or how the variable is used. Now, that ownership could be more complex. It could be many layers deep, but we don't need to really worry about that at this stage. So the things we really want to avoid, why we have to have this, we have to enforce the ownership, is that we don't, for example, want the vector to uh, go out of scope, in which case the vector itself maybe would get overwritten or would be removed, because then myvec, if we tried to use myvec, that would be pointing to something invalid or maybe nothing, but we wouldn't know what what that would be. So I've got to avoid that. That's the idea of the dangling pointer. The other problem is that if myvec, the variable, goes out of scope, then obviously we can no longer use that. But we, at the same time, we want to make sure that the vector that the myvec owns is also removed. Otherwise, it's just going to get left on the heap, and there's no reference to it. There's the variable that is effectively that is owning it no longer exists, and so it's just left there, kind of orphaned and not being cleaned up. So we have these rules about ownership. So any value in Rust has a variable that is its owner, and there can only be one owner at a time. And when the owner goes out of scope, then the value will be dropped. That's an indication that that value can then be removed from memory. So you've got this example piece of code here where we've created a string on the right-hand side. So this is creating a string from a string literal. So we've now got a string object, and strings are kept on the heap. And we're assigning that to a variable s here on the left-hand side. And you can think about the scope of the variable s. So that is scoped by the curly brackets that we have here. And what that means is that until we hit this curly bracket here, that the variable s is still in scope. So we can do things with it, which means that we can use the variable to modify or to do things with the string. Sorry, so it's mutable, but we could use that variable, and that is that's owning the string, so that everything is fine until we hit this curly bracket here, at which point the variable s goes out of scope. And what that means is that we can no longer access that string that is on the heap, but also the compiler knows that at that point, then that string on the heap is no longer needed. Okay. Now, some simple items exist on the stack, and so when we refer or when we make an assignment, we can just copy those values and everything works really in the way that you would expect it to work and that you've seen things working in other languages. And the data types for which that is the case are the simple ones such as integers or bools or floating points, etc. But there are different rules apply when we have data types such as string. And for things that are going to be on the heap, then these ownership rules apply. And when we do an assignment, so you see here that we've got a variable A, and then we assign that to variable B on the second line. That could be a copy if these are simple types, which in this case they are. But if it's a complex type, then it's not a copy that is happening, it is a move. And this is a different concept. So if we're doing a move, what we're doing is we're changing ownership, we're transferring ownership of the item that we have. So if you take these three lines of code here, we start off with, on the right-hand side, we're creating this vector, and then we're assigning that to the variable a. So now a is the owner of that vector. Then on the second line, we do a move. Because of the data type, it means this second line is going to be a move, and it moves ownership from A to B. So B is now the owner of the vector. Now, if we try to use the variable A again, we would get a problem because A doesn't own anything at this point. So if we try to do the assignment on the third line here, then that's going to throw an error because the A is no longer valid. And in fact, the compiler would be telling you that that's the case, that you can't do that. So for complex types, you have to be aware of when you are moving, when you are transferring ownership. And that's sort of straightforward in those three lines of code that I've shown you here, but then it can get a little bit more tricky to see when we do other things, such as calling a function. So I've got the example here of some code where we've got a function here, which is just called g, and that has one parameter called x. We're not bothered about the data type here. And then we're going to do something with x within the function. And imagine that you have a loop, and within the loop, you are calling this function g, and you're passing in a variable. So we're going to be assigning that to x within the function. Now, if we do it like this, if we start out, we've got some variable a, we assign something to that variable. It doesn't matter about the data type here. But then a is owning some value. Then we go into the loop and we pass that into the function g. So the first time we do this, everything's fine. So what it means is that x is going to then be the owner. We're moving for a complex data type. We're moving the value so that x is now going to own the value that a previously owned, and then we can do things with that within the function. But then if we loop around again and we try to do the same thing, well, we're going to get a problem because a no longer is the owner of something that we transferred. We did a move, so that transferred the ownership. And in fact, the item itself may have been removed because x will have gone out of scope at the end of that function anyway. So yeah, this is going to be a problem if we do that. So we have to have some way to do this, a better way to do this. We have to be more careful about doing this, and we'll see better ways to do that in a second. In fact, we'll see better ways to do it now, which is to use references. And if we didn't have references, then our code would be very fragile. It would be very difficult to uh, do the sort of normal things we want to do, such as calling functions, etc., because we'll be transferring ownership all the time, and that may not be what we want to do. And so references give us a flexible way to handle these types of problems without making things fragile. And what they allow us to do is to interact with objects, but without taking ownership of that object. Okay. And we write them. The syntax for a reference is a special syntax using the ampersand. So we can create a normal variable a, but if we want to create a reference, then we put an ampersand in front of that. And if a has type t, data type t, then ampersand a or ref a has type ref t. So, excuse me, the data type goes with follows into the reference there. So what do we mean by a reference? Well, it allows you to refer to a value, to interact with that value, but without taking ownership of it. So what that means is that when our reference goes out of scope, that's not going to force the value that we are referring to also go out of scope. The ownership is sort of being controlled elsewhere. Whatever variable was the original owner of that value is still going to be the owner. And so the value itself, the lifetime of that value, is being managed and dictated by the original owner and not by the reference. So this helps us out a lot because it means we can use references to interact with objects, but without worrying that we are taking ownership of that object. Now, we still have to be careful though when we're using references because we have to make sure that the reference is still referring to a valid object. So the reference itself must not outlive the thing that it is referring to. So if you've created a reference to something, but the owner of that the thing you're referring to, the value you're referring to, if that owner goes out of scope, you can no longer use that reference safely because that reference is not pointing to something valid anymore. All right, so that's the general idea about references. Now I'm going to introduce a distinction. So there are two types of references. It's easy to confuse these different types with the idea of ownership. So please don't do that. So references do not take ownership of values. And both of these types are the same in that respect. But we do have two types of references. The first one, I guess the most common one, is what is called a shared reference. And what this allows us to do is to read the thing that we're referring to, but not mutate it. And because we're not changing it, not mutating it, then we can have as many of these shared references as we like. Okay. Now, the second type of reference that we have is a mutable reference, and this allows us to modify the value that we're referring to. But because we are going to modify it, we have to restrict how many of those references we have. Otherwise, we could get into concurrency problems. So we can only have one mutable reference to an item at one time. But we can have as many shared references to an item as we want. And the way that we specify that a reference is mutable is that we use this syntax, the ampersand mute, when we are declaring that reference. And then that means that the reference that we get is going to be a mutable reference. Okay, but don't confuse that with ownership. Both types of reference are not taking ownership of an item. Even a mutable reference doesn't own the item it's changing. So it's not controlling, excuse me, the lifetime of the item that it is changing, that it is mutating, but it is allowed to change it. So we've got an example here. We again we create a string. We've got a variable that becomes the owner of that string, our variable s here. And then we want to be able to change the string. So we create a mutable reference to this string. And the mutable reference we're calling s1. And then we can use that to append a string literal to our original string. And we can print that out and everything is fine. But yeah, be aware that this S1 is not the owner of the string that we have, not the owner of this value. That is still owned by the variable S. So we can do that, but if we tried to do this next example, we would get a problem because we're trying to create two mutable references that are active at the same time, which we can't do. It will not let us have two mutable references. We could have shared references, but not mutable ones. Okay, and you've got another example here. doing that. So we've got a couple of functions. One is using a shared reference as when we are declaring the variable within the function, and one is using a mutable reference. Another way, or we also say when we're creating a reference, we say we also call that borrowing. So that's why I've got the borrow here. So we've got two situations here, two functions. So the top function is just allowing us to read the string that is being passed into the function. And in this case, we're reading the length of the string. The second one is allowing us to change the string, to append something to it. And then the main function here calls these two functions. So we start off creating a string and assigning that to a mutable variable, and that is the owner. And we can then use our calculate length function here, and we pass in a reference to that string. So we do refs passed into the calculate length, and we can print out the result of that. And then we can modify the string by calling the change function, and we pass in a mutable reference to s, and then that allows us to add to append an item to our string, and then we can print out the result of that. Okay. Okay, let me just check the Slido. Okay. Okay, I think we've got answers to everything, so that's good. The opposite to referencing, if you have a reference, we can dereference it by using the asterisk operator, as you can see here. So this is just a couple of examples where you've got a reference, and then you're using the dereferencing operator to get back the what that is referring to. Okay, but that's I guess that's not as common as using the references. This idea of borrowing and doing maybe a read-only borrow is very common, because that solves the problem that you may have. You want to pass some item into a function and let the function read details about that item, but you don't want to have that function or the parameter within the function taking ownership of the thing you've passed in. So doing a borrow, passing a reference to the object is going to solve that for you. Okay. I mentioned strings, so yeah, these are complex types. They made up of the bytes within the string themselves. They also have a length and a capacity. So the length is the number of bytes that we currently have within the string, and then the capacity is the size of the string that we can potentially have. Okay, so the length is always going to be less than or equal to the capacity, and there are methods that you can use to get those details if you want to. You saw that a common way to create a string object is to uh, create it from a string literal by using string and then the double colon syntax and from, and then providing a string literal, as you can see there. Okay. All right. I'll start to talk about trace, but I don't think we'll be able to cover all of this in the remaining time. We've only got a couple of minutes left, so but I can start to talk about them, and then we can come back to this tomorrow. So traits are similar to interfaces that you will have seen in other languages, and they allow us uh, to define the behavior that a particular data type can have, and also to allow us to um, collect together data types depending on the type of behavior that they have. So it's a way of, yeah, making our code more concise and neater by and more general, I suppose, by allowing us to specify the traits. The way that you define a trait is shown here. So you use the trait keyword, and then you give the trait a name. So in this case, it's going to be called summary. And then, and I'm sure you've come across something like this with interfaces. Within that, we then can specify functions that will be defining the behavior of the thing that is implementing the trait. So by providing these functions, we're restricting or defining what behavior our item is going to have. So what this is saying is that if something implements the summary trait, then it needs to provide an implementation of a function, and the function that has to be implemented has to have this signature. So it has to be called summarize. It has to return a string, and then I'll explain in a second what the ref self is about. So we can create traits with a number of functions, and that's a way that we can then provide implementations of that trait, and then we know that that implementation is going to behave in a certain way because it's going to have it's going to be it's going to contain functions, and those functions have a particular signature. So it gives us knowledge of how that thing is going to behave because it is implementing a particular trait.